All right, listen up, come on. Let's get this over with here. We have the integral of sine of 1 minus 2y over here. Now, remember, we are going forwards and backwards, but we can also employ our checking system to make sure we're integrating properly. Remember, that sine in the integral will give us negative cosine. So why don't we start with that? The inside will stay the same, as this is the inside of a function. There will be no change to the inside of the cosine during the derivative. Now, remember that we have 1 minus 2y inside of the function. So as a note here that I can write for myself, okay, note that when we take this derivative, we have a negative 2y coming out of the function, because chain rule will have our answer always output a negative 2 from the y. Again, that derivative respect to y in our equation is going to give us a coefficient of negative 2 that we must account for. Remember, when we're accounting for this, we can't change anything inside of the integral, but we can leave it on the outside of our answer. And so with that negative 2, the negative 2 has nowhere to go inside of this integral. So what will we need to do to cancel that out? Well, by taking the next step here, and the negative cosine of 1 minus 2y, but now we have to deal with that negative 2 coefficient coming out. Well, how about instead a negative 1/2 coefficient to cancel with that derivative? And so with a plus c, this looks pretty all right to me. But why don't we go ahead and take this guy's entire derivative so that we can confirm that we are indeed on the right track, or if any other changes must take place. So let's start. The derivative of negative cosine, thankfully, goes to a positive sign. The 1 minus 2y stay the same. And then with our chain rule function, we're going to have to go and take the derivative of this guy, the 1 minus 2y. Thankfully, our note took care of that too. A negative 2 will result from that derivative. And lastly, that negative 1/2 coefficient that we left outside is going to be waiting for us. The plus c, of course, going to 0 from the derivative. Now, looks like we just made the right chess moves over here, because we have fully anticipated the negative 2 canceling with that negative 1/2 that we gave out earlier. And when you look at that, this thing does match up exactly with the start of our integral. Is this really that hard for you? Man, this was meant to be easy. There's a reason why we made integration in the first place. Oh, these trig functions are going to be the death of so many students, but they don't care. They're just going to go about thinking that they can think that they are something else. Oh, I can handle it. Oh, there's nothing I need to worry about. No! You need to study this kind of mindset. The negative cosine as a result of sine being removed from the integral. So let's clean this up as a final answer here, because we have a lot of coefficients milling about. That's going to be a positive 1/2, because those negatives cancel, of cosine of 1 minus 2y plus c. This is the result from this example problem. Good. So with that, we'll do one more, and I'll kick you out of my classroom, because I am seriously getting close to the end of my rope here with people complaining about these types of functions. Is my integral? Oh, it was right there. Okay. Nonetheless, though, we have this kind of integral waiting for us on this example. When would you look at that? We have both a sine and a cosine waiting for us inside of the integral. Ooh! How could we ever do anything like that? There's no product rule in integration. But I think you might have forgotten that our strategy right now is that we will take a note as to how the things are related during our steps checking our work. Imagine that, thinking one step ahead of the problem. Who could ever do that? Most of the time we'll just stare at it and just go, "Excuse me, I can't do that. This is too hard. Absolutely not. I'm not here to listen to your complaints. I'm here to do these kinds of problems so that you can follow along. So, why don't we have a note here? Because this is going to be quite special. We have a sine squared and a cosine. But always remember, of course, that sine's derivative, especially in our case of x over 2, will give us a cosine of x over 2. Thankfully, all positive, and now with that coefficient of 1/2 thanks to chain rule. This should be quite helpful, given that sines will give us positive cosines, and also with the fact that the sine has a higher exponent while cosine does not. So, what does that lead us to conclude? Given that we have a sine squared, we need to bring that down a notch from where it's ending up at and raise it to one more power. Power? Is there a power rule hidden somewhere here? It looks like it. So, why don't we have this? Let's do an experiment here. Why don't we go ahead and think about having sine to the third power x over 2. Remember, we can check our work and make our adjustments accordingly, especially if there are coefficients missing. So what if we just, as a bit of entertainment here, think about the way that this will derive if this were the basis of our answer for this integral. The sine to the third, well, we do have power rule in here that 3 will come down as a coefficient. It becomes sine squared x over 2. And now chain rule is going to peel this onion one layer at a time. We had the power rule coming in. Next, we must take the derivative of the sine of x over 2. And would you look at that, our note comes in handy just right there. We'll have cosine of x over 2. And lastly, of course, we have our coefficient of 1 over 2. Well, so let's clean this up here and see what we have. And would you look at that, we have something that's awfully close to what we started with in the integral. One step closer to where we need to be. We have everything lined up except for no coefficient. So, this is a match, that's a match. Very good. We have everything we need over there. It's just that this guy has got to go. So what can we do here? Well, obviously you realize that this is simply a numerical coefficient. There are so many coefficient rules in both going forwards and with our derivatives and going backwards with our integrals. Looks like all we need to make this square off is that we need a 2/3 coefficient to simply cancel with our proposed answer. So why don't we look at it this way? We started with sine cubed. Remember, this is where all of our checking began. So it looks like going from here to there was a good idea. We just need a nice friendly coefficient waiting for us such that we can keep all of our answers intact, just have that number in front change a little bit. And let's have a plus c because this is the result of integration.
This doesn't look like integration work.
It does. We are going backwards from some proposed answers into some real answers after some fine tuning. You don't believe me? We'll just take the derivative of this one more time if I really need to get it through you that this is the correct form of that integral. So we have 2/3 waiting for us as a coefficient. We'll then have 3 come down from the exponent spot for the sine. We'll have sine coming down as power rule dictates, giving us sine squared of x over 2. Then we need to take the derivative of sine of x over 2 because of chain rule. Then we'll go into a positive cosine of x over 2. And lastly, we end up with a 1/2 because the derivative of x over 2 will be the last step of our chain rule. Plus 0 because of the c going to 0. And would you look at that? The 3 cancels out with the 3 in the denominator. The 1/2 gets removed because of the 2 coefficient. And everything matches up here in the way that it should with the start of our integral. Don't you feel so much happier now, knowing that I can stop yapping about this and you can start working? Look, there's only a few more rules left, and then hopefully we can get to some real word problems. Huh? Word problems? That's right. We'll go over some word problems soon enough with our ability to integrate. So we better see some improvement next time, because I am seriously running out of time here going over these kinds of basic things with you.